Briefly introduce our speaker today. Kuang Shi is a associate professor at the Stanford Business School. I'm not going to say too much except mention two things. He received a George Nicholson's prize from Informs while he was a master's student, and I think at that time was many of us were very shocked. A master's student, not PhD student, received a Nicholson's prize, very prestigious one. The second thing is that he recently received a Rising Star Award from Sigmatrix, and that's a testimony of his status in the community. So Kuang, I let you take over to give the talk.
Great, thank you, Jim. Thank you for the very generous introduction, and thanks to everyone. I was telling Jim, I think it will be really cool to visit in person, but nevertheless, it's still really exciting to talk to all the colleagues and look forward to the meetings later today and tomorrow. One quick question on the logistics. Is the meeting recorded or?
It's being recorded.
Oh, it is being recorded. Okay, cool. Just want to make sure because someone asked me if it will be available offline. So. All right, and I know the meeting is about an hour, and I would try to plan to have this for about 50 minutes or 45 minutes, and hopefully allow for some questions. So feel free to interrupt, just speak up. Okay, so so today I'm going to talk to you about a topic that's I find it quite exciting. Been working on since about 2 years ago, and this is joint work with my colleague Stefan Lager. And the title will be Experimenting in Equilibrium. A little abstract, but hopefully I'll manage to contextualize most of that later. So maybe starting with something a bit more high level, the general question that we're interested in are of experimental design for a large scale system. And specifically a lot of platforms and companies that these days are really interested in using experimental design to figure out what kind of product, what kind of treatment, what kind of policy is best for performance. Now, traditionally, this type of experiments are designed using so-called randomized controlled trials, or as it is known in the tech industry, A/B testing. Now, we've seen that a lot of these trials these days are being used in a system with lots of interacting participants, such as a kind of online economy or platforms. And as I will show you in a bit, it turns out this classical paradigm randomized controlled trials is quite difficult to be deployed in such interacting platforms. And sort of this sets the stage of the kind of question we want to understand, which is really how to do good, solid, effective experimental design in an interactive environment. All right, so maybe just to be concrete, I will present to you the following sort of motivating example. And this indeed, it will be the backbone of our actual model. It will just be a bit more informal at this point. So consider the following toy version of some sort of a sharing economy. Let's say a platform wants to satisfy a certain demand by recruiting freelancer workers to work for the platform and satisfy the demand. Now, every day, the platform will commit to a certain payment, PI. That is to say, for any unit of demand worker I will serve, this person will be compensated by the amount of payment, PI. Now, on seeing this offer PI, each worker then kind of calculates how much they value this work and how many workers they expect will be out there, and decide whether or not to become active and join the platform for that round. Once that's done, we have a bunch of workers who decide to become active, and the platform then just randomly allocates all the demand across these people. Now, the key question here could be, how do you pick the PI so as to maximize platform utility? If the PI is too high, if the PI is too low, well, maybe nobody would join because nobody's making money. Well, the subtlety here is if PI is too high, maybe that's also not so great because people will, in fact, expect that at some point PI won't have effect because more people will join, and therefore each worker will get less work, so that the kind of increasing utility is actually for the workers not really linear in PI in some way. So it actually turns out to be a pretty subtle question to understand. How would you find optimal utility here? Right. So anyway, so that's a generic question. So now let's see what kind of options do we have in understanding how to find this price. Now, first thing to note, we are in the system for now that we don't really know all the parameters of all the workers, their utility functions and whatnot. For if we do have all that data, maybe we don't have to run any trials, we just optimize. So let's say we don't. So what can we do? Idea number one is to run a classic case-controlled randomized trial. That is, I'm just going to give different workers different payments and see how each person responds to that. It sounds simple enough. Maybe from there, we can figure out their average utility function and optimize. But now the issue here is this won't work because of interference. At least it's not going to work in a very simple way. That is, workers who are paid more are actually likely to become more active and therefore cannibalize demand from others. So induce some fairly intricate interference patterns across them. Now, idea number two is maybe, okay, so maybe they compete with each other. Can we find environments where they do not interact and do the same thing? And in fact, this actually is done in the industry. And this is typically known as randomizing by cities. So here, maybe I would just identify only cities, and for each city, I will give all workers the same PI. Well, clearly, different cities presumably don't share the same market. Maybe from there, I can at least get an unbiased estimator of what the PI, the impact of PI is. Now, the big problem here is though, now you go from a sample size that's the number of workers to the sample size effectively that's number of cities, from potentially millions to a handful. And that's really at the cost of significant loss of power or significantly increased variance and accuracy. So this work, we're going to try to advance a third idea beyond the naive randomized control trial and a randomized across cities, which is to actually model and therefore explicitly correct for interference. And a key technique and key tool that we're going to leverage is to show that in some sense, under reasonable assumptions, we obtain a so-called mean field limit in this type of interactions. And in that limit, we can actually understand pretty well how interference works. And with the right type of experiments, we can extract the key information that we need. Okay. All right, so I understand the audience actually has a lot of experts in causal inference. So I will first preface by saying the next two slides, I want to step back a little bit for the rest of the audience to maybe further just highlight the intuition behind what could go wrong in a concrete example of ignoring interference and do some naive form of randomized trials or A/B testing. Okay. So for now, let's back step a little bit, just see, okay, what exactly goes wrong with the naive randomized control trials? I think this is a fairly interesting and intuitive example. So let's say we want to understand the impact of vaccination. And the story is actually not funny because we wrote this example before COVID, but then COVID happened. So I guess now everybody feels like they have a PhD in this topic, so maybe even better. But let's say there's a very naive model of vaccination. So a estimator is trying to understand this quantity R of mu, which is the probability of a random individual getting the disease conditional on, in the ambience environment, mu fraction of the whole population vaccinated, right? So maybe as a policy designer today, it's actually a very relevant question is, I want to decide, is it worth it to vaccinate everyone? So what is R1 compared to R0? Well, I know it's probably better than R0, but is it worth my investment and risk and all that, right? So that seems to be a very valid question. So here's what one could do for naive randomized control trial. I pick a small fraction of people, right? I vaccinate them, and I leave the rest of the population unvaccinated for now. And I simply measure within that group R1 and R0. Just within the group I did my randomized control trials on. Okay. And then I would just take the difference between these two as my estimate for what would have happened if I did vaccinate everyone in the population. Okay, sounds reasonable so far? Okay, cool. All right, so now, actually forget about this plot for now. I will go back to it. So let's call VAB be a person's risk when their own vaccination status is A, while in the society, the fraction of people vaccinated is B. Okay, so I can rewrite this quantity of interest, R1 minus R0, R0 minus R1, as V00 when I'm not vaccinated, nobody else is vaccinated, minus V11 when I'm vaccinated and everybody else is vaccinated, right? That would have been the correct number. But what happens with RCT? Well, here's a problem. If we do the naive version of that, we get V00, that's fine. But here we get V10, that we're really just measuring the marginal effect of vaccinating one person, assuming nobody else is vaccinated. Wait, so clearly V11 is actually different from V10 because of herd immunity. If more people vaccinated, you actually lower your own risk too. So that's essentially what this plot is showing. Here you see two curves. So the solid line is the reality. If you were to vaccinate more people, this is what you would see as sort of like the effect on an individual's risk. But if you ignore that and you run a randomized control trial in a small community without thinking about the interference later on, the herd immunity, then you will see something like the dotted curve, which is much more pessimistic. And therefore, at the end, RCT gives you a gap right here, whereas the true gap is actually much bigger to the right. Okay. All right. So,
question?
Yeah.
Yeah. So in the naive RCT, there is sort of an epsilon that has been vaccinated. So, could I think about basically exactly what you're doing here, but in the second expression, r hat 0 minus r hat 1, it would be
absolutely
minus epsilon.
It should be like epsilon, but for now, let's just pretend epsilon is like,
okay, great.
1 over square root n. So yeah. Basically 0. Yeah, absolutely.
Okay. Yeah, thank you.
Yeah. So I don't actually know if this has actually happened with COVID, but I suspect maybe this could play a role as well. But which is not a bad thing because at least this is a pessimistic estimate, but in any case, it's not a correct estimate. Right? All right, so this example hopefully convinces you that interference is a thing that can happen in fairly natural systems. Now, and you can imagine similar things would happen in a market. And here we're talking about if you incentivize people and they all show up and suddenly supply is dwindling, and we will see interference effect that we would have not seen in the small RCT. So classically, such a problem has often been studied in causal inference under a graph model where each individual is carefully modeled as a node on a network. And here the general assumption is they interfere each other through these links. And therefore, to control for interference, a standard approach is by cutting up what's called exposure graph, just to make sure the way you perform experiments is in such a way that people who do interact with each other are sort of not assigned different treatments or whatnot. So they hopefully don't actually interfere. So it's a very similar philosophy to doing experiments across cities so that whatever you actually do not talk to each other, right? So that's one approach that's classic. Now, we're gonna try to ask the following main question now, given this backdrop. Can we design more powerful experiments, powerful in terms of statistical power, that are robust to interference, in fact, very high level interference, but the approach that we're gonna take, the assumption we're gonna add, is to use a bit of modeling. So that sort of is the main goal here. Okay. All right. All right, any questions so far on the overall framing? Sorry, I keep looking to the right because all your faces are here, so I'm not looking away. Okay, cool, no questions. All right. So this slide is actually very important. I wanna be careful and make sure I get the point across. We clearly have to make some assumption. What kind of assumption we're gonna make? Our key assumption is that yes, there's interference everywhere, people all interact with each other, but such interaction has a certain structure to it. And the structure is such that the interference is mediated by the participants' response to expected revenue. Okay. Okay. And more abstractly, the requirement is such that there's essentially one or two key statistic that captures all the interactions in the network. So it's not like I interact with the individual in some random arbitrary way. We all contribute the formation of this expected revenue or expected demand inside the market, and that quantity in turn affects everyone else's behavior. So you can imagine the market sort of work like a star graph. We all connect to a middle node, which has some key statistic, and the middle node then controls my payoff and utility and all that. So I interact with everyone, but through this middle central statistic. Okay. So this is an assumption, but it is quite aligned with some empirical evidence in the ride-sharing context. And also philosophically, it's very much inspired and similar to the so-called sufficient statistic approach in economics, where it's somewhat in between a very reduced form model and a fully specified model, where we do have a full model, but instead we just analyze some very important key statistic of that model, and without just estimating every single parameter there. And all these considerations essentially goes into that observation that our interference in this model will be due to demand cannibalization, which is more people joining, then less demand for everyone, and therefore is mediated by total supply to the system. So that kind of forms our key statistic.
So a question here.
Yep.
So how to think about this in the context of ride sharing case? That's a driver, if you promise PI, right? But it really driver is care about how much she can get.
Absolutely. So Jim, maybe
yeah.
I would postpone you for a slide, because the next slide I would define a formal model, because right now it's still very high level. I haven't introduced it.
Sure.
Hopefully it will become clear.
Mm-hmm.
Cool. All right, so maybe enough motivation and high level discussions. Let's actually dive into the model. I'm gonna flash out this simple example I told you earlier, but this time in the actual math that we're gonna deal with, okay? All right, so this is a step where things will manifest. You can imagine every day the following things happen. So the platform first chooses a distribution pi and promises a payment pi to driver or worker I drawn from pi. Okay. Then a fraction having seen this number pi and knowing pi, these drivers are sort of like being aware. If a fraction, then people choose to join, and if a fraction mu of all workers become active, then the expected demand served by any worker, if they become active, we'll call that Q of mu. Okay. They become active, and then demand is carved up by them in some way, and per person gets Q of mu. Good. So now knowing so, this is the important part, the workers will make the following decision. They will have some outside option BI, which they have internally, we don't know about it, such that given the distribution pi, we'll assume that the ith worker will become active with the probability f of BI, it's sort of their utility function or choice function, as a function of pi times Q. Okay, so here I'm just giving you one specific example of this type of function. For example, a logit function with offset BI and some parameter beta and so on, but this in general could be very general increasing functions in the argument. Now it's very important to notice pi times Q is simply the expected revenue. It's what the worker thinks they will make should they join the market. They will promise pi per unit of demand and Q amount of demand based on their belief of how much they will get in the future. And finally, notice, how do we define mu? Well, mu is something that people believe will manifest. Then the system, we call that in equilibrium, if the fraction active worker is indeed consistent with the expected number of people that would choose to join. So if mu solves this equation, we call that mu a equilibrium amount of demand per person allocated. Any questions on this setup? Cool. Okay, so I just want to maybe highlight a bit. It turns out mu of pi is a very, very important quantity. Sort of is the crux. The key that we want to understand is how to use essentially pi to manipulate mu, and how does mu depend on pi? And that's the key thing we want to understand. Once we understand that, there is a way to find the optimal price. Okay. All right, so the next key idea, so once the model is set up, there are essentially two key ideas after this point. Key idea number one is what type of experiments we're going to run. That's question number one. And question number two is once we run it and collected the data, how do we interpret the result to eventually get at this kind of total effect of how to then optimize the price, right? So I'll tell you these two things. So the first thing is what kind of experiments we're going to run. So we're going to run experiment, so-called the local experiment. We're going to independently perturb each worker's payment. So here I'm telling you a specific kind of pi we're going to use, which is some reference price P, just a number. For example, currently everybody's getting $10. Then to run experiment, I will randomly perturb their P plus minus 1 times eta. Well, actually, this is not really eta. I forgot which Greek letter this is. I think was, I think psi is the right word. Okay,
Zeta.
so
That one is zeta.
Is that zeta? Okay, maybe that's zeta. All right, so let's go with zeta. Apologize to all my Greek friends. So, so zeta is a small number, let's say 10 cents or 50 cents. And I'm just gonna give everybody plus or minus zeta randomly. Okay, so here's the key observation. Why do we do that? We do it because if I perturb everybody by a small amount, plus minus zeta, then clearly you can imagine in the network, the average payment is roughly P. In fact, it's exactly P in the expectation. So if the mean field model works out right, later I will show you, then doing this experiment does not shift the overall equilibrium state of the system. Just adds a bit of noise to each individual, but the mean field equilibrium stays the same. We can show that later. Interesting. So if this stays the same, they cannot interfere with each other because interference only mediated by changing this key kind of like expected revenue quantity. But if the matching probability didn't change because I didn't really change the average price offered, maybe I can essentially sever that interference and learn something that is not being contaminated by that. Okay. So let me be more concrete. So suppose we offer this to every worker plus minus eta, then I can simply look at their response, did they join the system or not, and run a simple linear regression on that. Meaning I regress the treatment if some person got the plus eta or minus eta against the actual realization if they joined the system and didn't join the system. So I will call this linear regression coefficient delta hat. Okay, it's some kind of sensitivity to this perturbation. So we'll call delta hat. It turns out to be an estimator of what's called marginal response of the workers to the change of their price. Okay. So what's interesting now is we can't estimate delta, but delta is actually not the thing that we're really interested in, because precisely the way we did this experiment is by severing and eliminating this kind of interference effect across workers. So what delta really measures is only if everybody else gets P and you get P plus 1, how much more are you likely to join the system? It's this very marginal concept where the environment didn't change, only you changed. So that's not what we want. What we really want is to understand what if everyone gets plus 1 or plus zeta in their treatment, right? However, now this is the second important thing now. It turns out, as I'll show you soon, so this is the experiment, we can actually, using the equilibrium model, to use delta to work out the final policy relevant intervention question. So far our experiments are done. This is the data we'll collect. The claim is, if you perform some analysis on this mean field model, the rest is calculation. You no longer need more experiments. Okay, and that's the sort of the second part of this result I will show you. All right, so at this point, I want to take a quick pause and maybe just, it's enough high-level thing. Maybe let me show you some simulation results of a very simple system. Just get some insight on how this actually works and how does it compare to some more conventional benchmarks. Okay, and then we'll go back to the actual theory. I just want to get you more excited about the result before I show you theorems and convergence and all that stuff. Okay, so imagine the following system. So I'm going to run a platform choosing payment to maximize some utility function U, same system I described earlier, and it's a horizon of 200 days. And there's no interference across days, so every day is this individual event. But per day, there's some demand fluctuation, meaning these BIs and the realization of the demand depends on some global factor that vary day to day. Did it rain? Was there a sport event? And so on. So there's quite a bit of a variability in the day to day. And on the left-hand side, I'm just plotting for you various primitives. So for example, if you increase payment, you can kind of see like fraction suppliers will become higher and higher, more people become active, but it kind of tapers out due to interference effect. And then demand per active supplier, you can see it dropping. Initially, everybody gets a lot of work, but if more people join, then per person gets less and less work. And then finally, demand served sort of like also saturates to some final total demand. And this is just calculation. This is from the actual model. And the learning algorithm doesn't know all these curves. Okay. And here is the true utility function as a function payment. Okay. And there's a tiny dotted line here is the optimal. There's a blue line is what you will get running experiments based on our method. And the red line is some benchmark, what we call global experimentation, which I will show you in a bit. But for now, suffice to say the blue is very, very close to the optimal. There's a bit of noise, but red is actually decidedly far away. Okay, so now what are they and how do we actually run this? So we'll consider the following, probably not very optimized, but later I'll show you theory to back up that this is actually about the best you can do. Global experimentation. Other words in bandits, people call it sort of explore then commit. So each day, we up to some days, we just randomize the price across some range. We measure the outcome. And at the end of the exploration period, you fit some function to the data you observed, you maximize that function, and you just use that price later. Okay. So that's global experimentation or explore and commit. And local experimentation will be using exactly what we did to derive a gradient on du dp. How does my utility change as my price gets varied? So up until now, I've already given you some overview of how to derive this delta hat marginal response. And I haven't told you how to then get to the du dp, but for now, let's say you can. And then once you get that, you simply run some form of gradient descent to iteratively improve your price from day to day. So in the next day, you will get a new updated price and you do local experiments around that price and repeat. And then you get this kind of a phenomenon. So on the left-hand panel, this is probably the most important data I'll show you, which is essentially the regret performance of various policies, the global versus the local experimentation. So on the cross is what we can get with this local experimentation approach. And you just get a very, very small regret. And on the red dots, let me explain what this is. So the red dots measures in-sample regret against future expected regret. So the blue is just in-sample because we never really explore then commit. It's just always sort of running the experiments. So for the red, I'm actually gonna optimize over where you stopped exploring. I'll scan over how long you explore. But regardless, you see this kind of a phenomena. Either you suffer a lot of in-sample regret, or you suffer a lot of future regret, or both. In fact, it's not even sort of like monotone in some way. So suffice to say, the red region is way bigger regret in both axes compared to the blue. Okay. And here, just to give you a sample path of how the blue comes about, as you run this kind of local experiment, then derive the gradient, you see fast convergence as you would in a simple gradient-based optimization scheme. You see this rapid convergence around and has some noise, so it kind of bounces around a bit. All right. Any questions so far for this example? Okay, so we've explained how the experiments are done. We show you some kind of numerical result, but to go further, we do have to now introduce the mean field limit. Because there's still this kind of big question, how do we convert the data we collected into the derivative of d utility, d price, the thing we want to know. So let me just bring in a bit more formalism. So we're going to adopt the following asymptotic setting where the number of workers will tend to infinity. So initially there will be n people, and across these n people, they will make decision who will join, and it will scale the system as driving n to infinity. So let me state a few assumptions. Assumption one is the worker, there's some daily variable that controls the weather and some kind of shock. Let's say the workers know that variable. And now assumption number two, that the market dynamics, how we allocate demand to the supply, only depends on the supply-demand ratio. This is just to make sure the mean field model is not crazy. It's not like, oh, suddenly if more people show up, I somehow change the way I allocate them. Let's just keep it simple. It's some function that look at the ratio between supply and demand to determine how much demand each person gets. The simplest one will be just divide them equally or something like that. Right? Okay. Now let's look at this regime angled infinity. I will state a few facts. These are sort of lemmas that can be derived under this model. The first lemma is equilibrium is always well-defined. So mu A equals E of blah, 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 mu A always has a valid solution. So this means there's a unique, well-defined mu that comes out of the interaction. And by the way, once you have that, we also see very easily that the number of people who become active will just be n, a binomial random variable with n trials and mu A per trial. Fact number two, and this is very important, now let's drive n to infinity, then the equilibrium, the mu thing, and all relevant derivatives of that, d mu dp, d whatever, I forgot some other variables there, dp, all of them converge to the mean field solution of those models. Okay. And this is really the most challenging part technically for us. And the very difficult part is the interchange of the limit and derivative for Q. If you remember, Q is the amount of demand each person gets in the nth system. And you can show that the derivative of that against your mu actually interchanges into the derivative of that in the mean field limit. And it's quite tricky because Q and mu does not admit very nice, concise, closed form expressions. We can't just take n to infinity there. So we'll use a result by Stein in 1981 that links the derivative expected functionals of random variable to a certain covariance that are easier to evaluate. There might be other ways, but this is one way that we overcame this difficulty. So this is sort of the kind of the more applied probability style convergence that people typically see in queuing theory and other systems. All right. So fact three. Remember that we are perturbing everybody's payment by some zeta amount, half and half, plus minus. Now, in this scheme, we're going to let zeta sort of go down to zero. So the payment perturbation has to shrink smaller and smaller, and we estimate this delta hat. Then we can prove that delta hat will converge in probability to this delta mean field again, mean field quantity. And this mean field quantity has a very nice and intuitive sort of explanation. Okay. And we'll refer to this quantity as the marginal response function. So let me interpret this function a bit. Okay, very short. All right, so the key insight is that, as I mentioned earlier, because these perturbations are zero mean and the zeta goes to zero, very, very small, in the limit, essentially the perturbation will never affect the equilibrium mu anymore. It's just like mu of P. As a result, delta actually corresponds to the marginal responsiveness of a single worker who assumes a unperturbed ambient equilibrium. Just pretends everybody else is getting P, just I'm getting something slightly different. Okay, so delta hat is not a consistent estimate of the average responsiveness if everybody were to get something different, but we will show that it can be corrected in the mean field limit. Jim, I think you're muted.
This is okay. Need to slow down a bit. This is difficult. Okay, very difficult. So first of all, this delta hat is whatever the quantity, or something that's important quantity. Is that something? It's measurable something, or the platform can measure, or something that.
Good. Yeah, maybe I should be a bit more clear about what OLS here implies. It's more like a stats notation. I was also a bit confused initially. So let me be more concrete. How do we get delta hat? Okay. You perturb everybody up and down by some small amount. And you look at who joined the platform. Then you write down essentially a linear regression model, which says response equals parameter times whether this person got +1 or -1, a variable, like linear regression style, y equal to ax, where y is that the person joined or not.
Yeah, that's fine. That's fine. But the thing is, right, if the person joining happens that day, right, it happens that day, there's no demand, right? There's no customer, nobody want to take a ride for some reason. Okay, maybe whether it's a sun shining, right? People go to beach or something, do not want to take a ride. Sure. So many people, many workers, drivers never been assigned anything. And then the next day they will not show up or something, right? Something, is that an experiment? Something need to be running sometime or just next day or just something? That's what I'm confusing.
Good, fair. So maybe, I think the better way to think about this, these are slotted experiments, maybe on the time scale of like a week or a month. So we assume period to period is a new thing. So remember this variable A that determines like sunshine or not, that thing gets regenerated every round. So in some sense, what they end up being allocated with already happened after this point. This is just, they see some state and they make their decision whether to join or not. And once they joined, we collected data.
Okay, so this doesn't require something multiple, right? Like a multiple days experiment or something, right? Is that something?
I think the point here is,
or this is something always there is some ideal situation environment, mathematical model environment, you just be able to calculate or what? It's, that's something that I'm, right.
I think the assumption here is the drivers do respond to the equilibrium state. So they make decision based on their belief equilibrium. Now, empirically, what I personally think could happen is they don't really think, there's not like they do a calculation about what they should do, but the market kind of converges in some way to equilibrium. And this is what they respond to. We don't have a formal convergence result to that equilibrium. We just simply assume that the driver uses equilibrium concept to make that decision.
I see. So something there's a compress there. So something that maybe 100 days in experiment, something you are just one shot experiment that somehow driver magically know the equilibrium or something, right? Response.
Correct. So it sort of makes this kind of game theoretic assumption that the players act as if they calculated equilibrium.
All right. Okay.
That's fair. Yeah, that's definitely an
quick question. Are you assuming some kind of smoothness for the utility function with respect to
yes. So, because otherwise gradient can be a little tricky to define. We didn't want to go through that.
And the fact that you're linearizing it, but I guess my sort of hidden question being in any system like this, I could assume there is a threshold style phenomena where, like, for any finite system, there is a discontinuity.
So let me comment on that. Actually, that's a very, very interesting question. We're dealing with it in a follow-up work as well, especially in economics. A standard model is everybody has a price. If it's below the price, they don't do anything. Above the price, they do something, right? It's a jump. So I think the correct criteria, which we don't use here, we just cheat a little bit more. We use a smooth response function. First of all, I don't think okay, good. Let me put it this way. I think the key quantity that you really need, which is a bit more general than what we have, is that the expected response of the drivers, so the drivers sort of internal value BI has a smooth or non-atomic density. So on average in the population, these response functions are kind of smooth, but individually, maybe the driver has a threshold function. So it's a completely fair point.
Oh, I see. Yeah, no, I was more worried about thresholds with respect to like the delays, for example, if the drivers slightly exceed the demand.
However, actually, I think in this particular model, because it's one shot, it actually doesn't matter because the driver's action right now is discrete, join or not join. So you can think of the thing as actually a threshold. It's a kind of synonymous, right? But indeed, it's an issue in a model that we're looking at where demand can be continuous. It's not a discrete choice. Then it matters whether it's continuous or discrete or not. Anyway, so that's a very good question as well. All right. Any other questions before I move on? Okay. All right. So in the mean field, everything nicely converged to the mean field counterparts. The estimate delta hat for the marginal response of these workers converged to the mean field marginal response. And fact 4, this is the very important fact I haven't shown you yet, which is that under all these assumptions, our assumptions, the marginal response function delta and the supply response d mu dp, this is the very important thing. If I change price, how would people's average behavior actually change? This is no longer a symmetric perturbation, it's just plain derivative, are linked through the following system of equations. In the paper, we actually give a very detailed interpretation of what these terms actually mean. But for now, suffice to say, why do we get this? Is precisely through the fact that there is equilibrium. It comes from the fact that a mu is a solution to a balanced equation. And then effectively, if you differentiate on both sides of the equation, you will see nicely delta P coming out as part of the input. And this essentially is, if you remember the equation condition is mu equals E of F, something like that. You effectively, in the mean field, differentiate both sides on P, and you will get exactly this equation in the mean field, where all the expectation falls apart and goes into their mean field counterparts. Now, it suffices to say, at the end of the day, this equation is simply a one equation, one variable system, and you just solve for d mu dp. So it appears here and appears here. It's a linear equation, just solve for it. Apart from delta p, which we don't know and had to estimate, all other quantities equation can be observed very easily. You don't need to do any experimentation for that. All right, so now we're done. After all these procedures, the main theorem then says, under this procedure, then this scheme gives you a consistent estimator of d mu dp as n goes to infinity. Okay, so that's the main theorem. All right, now just to bridge the final gap. So far we have this d mu dp, which is how people respond with respect to price. Ultimately, we care about money or income or utility, not just the response. But it turns out this very last step is not too difficult. Once you know how people respond, you can kind of work out the impact on utility. So once you have d mu dp, to get the utility derivative, follows from calculus and some calculations. Okay. All right. So now let me just wrap everything back together and propose to you what we're advocating the platform actually do. So this is like what a platform actually does to run experiments. So every day, so we're going to run some kind of mirror descent variant on this. It's a very simple mirror descent. So every day the following happens. Well, by the way, when I say day, to Jim's point, it's not really day. Maybe it's some experimentation period. You would deploy the randomized perturbations around P and hold the perturbation fixed throughout this whatever period is. From there, you run the local experiment to estimate delta by running the linear regression. Then using the mean field model, you convert delta into an estimate of the utility gradient using the mean field limit. Once you have the utility gradient, you plug it into some generic gradient descent algorithm to get the right rate, we were using mirror descent, but I guess you can use some other kind of descent. Then under the right assumptions on various functions, such as strong concavity, then we get a very nice rate of convergence to the optimal price and to the optimal utility. Now, step 1 through 3 is really the innovation here. And once you're at step 3, you can do whatever you like with the gradient. Right? All right, just to drive the point home, as you can probably expect at this point, once we have a very nice convergence result to the gradient, you can use existing results to get strong convergence rates. So for example, you can get 1/t rate of convergence in regret and in the error of estimating the optimal price, both 1/t. I do want to make an argument, though, that this is a very important comparison. Remember, I kind of showed you this explore and then commit policy earlier in the simulation. And that's a sort of a proxy for other more sophisticated bandit algorithms, so-called zeroth order bandit, continuous arm bandit. For those algorithms, they essentially treat the entire city as one block. They set a price. They observe a noisy realization of the utility, noisy because the weather, this A variable is noisy. And then they proceed to pick the next price, observe a noisy observation, and continue. So this is what's called continuous arm bandits. And you might argue that the explore commit policy I showed you earlier might not be the most optimal. Well, by the way, they're actually pretty optimal if you optimize over how much you explore. But even if they're not, what it turns out is the optimal regret in this type of problems actually scales as 1/√t, even under the best policy. And even if we know that the utility is quadratic, it's by a result of Shamir in 2013. So it just goes to say, essentially, by using local randomization, we get gradients and order magnitude faster convergence. So we get 1/t, and if you use even the most sophisticated sort of a continuous arm bandit problem formulation, you will only get 1/√t at a much higher cost of experimentation. All right, so I want to leave some time for questions, so I will maybe skip the next few slides. But one thing I do want to mention, the next few slides all address this question of how general is this model? And the question is a big question, but we can highlight at the very least, even in the existing model, you can generalize beyond just having expected revenue to plug into the driver's response. So in the paper, we offer an approach called generalized earning functions that you can do kind of cool stuff beyond that. For example, you can model more arbitrary risk aversion, maybe drivers like safe payoff, they don't really care about a lot of payoff. And you can also model very well supply side surge pricing. A bit more complicated, but you can model that. And here's some math on how that actually works out. It's just a more complicated balance equation you need to solve. And some numerical experiments. To the left is the experiment I showed you earlier with a simple earning function and decision function. To the right, we sort of built in a model of surge. The whole point here is things don't really change that much. The gap and separation is pretty much the same. If anything, the surge even penalizes the global experimentation a bit more. All right, so a quick summary. While most work on design with interference, experimental design focuses on no interference, but this assumption seems to really fail in a marketplace setting. Probably not failing in maybe some kind of drug trial, but in market, it really is not the right assumption. And there are multiple approaches for addressing this. And we showed that in some sense, we can actually deal with very strong interference, namely everybody's interfering with everyone, by using some lightweight modeling and get very strong power out of it. Now here is maybe like one way to view how our work and our approach differs from the existing graph cutting approaches in causal inference. So for graph cutting, you can look at 2 dimensions. Typically, you will have to assume that the interference pattern is sparse. Not everybody interferes with everybody. And it's known, the graph structure is known. And you can kind of like do the cutting and control for that. But the benefit is they can handle much more general type of mechanisms, type of interference. For us, we call this model-based. You can actually deal with complete graphs, everybody interfering with everybody. Complete graph is a quote unquote, is sort of global interference. but we lose a bit in the modeling generality. So we will assume some kind of mean field dynamics arising. Without the mean field, maybe it will be harder to draw any kind of conclusions. Right? And suffice to say, there are lots of interesting questions after this point. Now, the final slide I want to show is maybe somewhat of a rallying call or advertisement. Rather, just in recent years, I've been quite interested in learning problems. As many of you know, I've been working on modeling of stochastic systems and queuing systems. And a kind of a theme that I kind of noticed, I feel there's a lot of opportunity that's presented by stochastic modeling, and in particular, more sophisticated limiting objects in stochastic modeling, when it's being applied to complex learning systems and dynamics. I emphasize complex because I feel this is an area that this community knows very well how to address. And I feel there's a lot more opportunities there in the statistics and learning realm. We have a few recent attempts. A couple of years ago, we wrote a paper on using fluid models to do experiment design with limited testing capacity. And in fact, I heard 2 weeks ago, my co-author Stefan was here in the same seminar and talked about another recent work on using diffusion asymptotics to study bandits. And sort of this work fits in the same umbrella, but again, here we're not using diffusion, but using the sort of fluid / mean field modeling technique for understanding interference. So I'm really excited to see what other areas similar models can be applied to. All right, so basically that's all I have to say. The paper is up on archive and I think forthcoming in Management Science, and welcome any questions.
Are there any questions here?
So, yeah, if I could ask, please.
Sure.
So, in thinking about your comment in response to Jim's question that these time blocks are essentially sort of let's have another go kind of experiences. But I think it is true that there is this memory as you move, say, on the daily scale, maybe even on the weekly scale. So I'm curious what would happen if you were in this kind of non-stationary environment where you're getting smacked every now and then by weather and stuff like that. But rather than looking for some kind of convergence in T, you use some kind of constant step size and you were looking just at sort of finite regret analysis over that finite T. Is that something that is plausible, or is it asking too much to be able to operate in a random environment?
So the current regret bounds we have are finite bounds. So in the classic bandit sense, the T is fixed, and for T you get a bound. The limit we do take though is the spatial one, which is number of people going to infinity. I don't know if that addressed your question.
I guess to some extent, but not the random environments. So, I mean, that there's just this heavy correlation or heavy dependence across every driver.
Yeah, that's a very good question. I think one kind of a consistent thing we've been thinking about, we hear a lot from others' feedback on this work is, how do you blend this learning process from some underlying mechanism that induce equilibrium to begin with? How do you kind of put them together? Right now, we just assume the equilibrium happens like bend, in a kind of abstract way how they arise. I do feel there's some evidence where this is a plausible model for if you run XP at a ride-sharing company for like a week or so, or maybe a month. And then people don't really compute the mu, but as they start to try, they're like, huh, interesting. Like I empirically observe, I get 10 rides per hour, and they would adjust to that over time. Now, then let's say next week you suddenly changed it, there must be some memory that carry over, but hopefully not too much. Maybe the first 5 days, people feel something, but later on they see, oh, actually I'm getting more rides. They update their mu. So one thing we're actually doing is to validate that. We're planning on deploying a game to actually run this with real people. And of course, it doesn't really address the full generality of application, but I think it will, to a certain extent, reassure some concerns on that front.
So could I just ask, it's a kind of a follow-up, which Sid, I see you're unmuting, so I'll get out of your way in just like 1 sec. When I think about the folks that I've encountered in ride hailing drivers, my sense is that they're driven pretty heavily by kind of random experiences in the short term, their behavior. So they choose, for example, when to operate during the day based on maybe, say, a week's worth of experience or something. So that would suggest that there's kind of this very noisy learning of mu. Have you thought, along those lines?
Yeah, absolutely. My personal take, I think everybody can have their take on it. My personal take is a design choice. So I think if the platform wants to, they can provide tools for users to estimate mu better. To give you one example, I think these companies do publish, send them a PDF on how much you've earned last month or something like that, as a way to reassure, like, they can make their best decision on how much to drive and how much they're actually making. I think if this becomes something actually companies want to do, it's not so hard to not to lie at all, but just provide the informatics on the app and say, oh, actually, I've been getting this much matching rate last week. I mean, as long as it's not untrue, I think people can make whatever they want out of it. So meaning they don't have to rely on people's mental capacity to track mu. They can just do it. It's something easily, the app itself can report it for the driver. And then the driver can make their own decision having seen that mu, which we do model. We don't assume anything beyond they have some random kind of utility function of some sort. If that's convincing enough.
No, it's certainly, it's moving in a good direction for sure. Yeah. Thank you.
Yes, I don't know if there's a technical question or not, but it felt like the main reason you're getting the benefit is because you're estimating the gradient at each point along with a single point. But like when you were using, like, so another thing that I could do is I could have some sense of like maybe the curvature of the problem. And even when I do global experimentation, not just like feed in some extra parameter, like I know this is some bounds on the curvature of what the revenue function looks like, and try to experiment based on that. And so are you saying that's not a good enough proxy for knowing the gradient?
So the bottom line here is, the distinction here is the following. If you do not use this local perturbation to extract gradient, the kind of power that we provide is in one sample, you get a gradient with much, much less noise than one would have gotten by sort of doing like a finite difference method. And the claim is actually stronger than that. In fact, if you don't estimate that gradient, which means you essentially just have a noisy zeroth order oracle, you query a function at some point, then these results in bandit theory says that not only is it bad, but even if I tell you the utility function is quadratic, you still get root T regret. It's huge. So there's literally no way. It's not the limitation of the particular policy I used in the simulation. It's a proxy, but essentially all policies will suffer. Essentially, it's saying that the power of having a gradient with low noise is so powerful, you really shouldn't let that information go. That's sort of the bottom line here. We're using the spatial diversity to extract this gradient. Yeah.
Interesting. Okay, I didn't know the thing about the quadratic, because yeah, there it almost feels like if I estimated well enough at 2 points, that's good enough. I can just
exactly, but with noise you can't. Without noise, yes, it's trivial. Quadratic just two points, you're done. But with noise, it turns out it's very, very hard.
Thank you. I don't know how we can remotely applause for you.
No worries. I've already seen a lot of hands coming up.
Yeah,
thank you all.
Yeah. Thank you, Kuang, and we hopefully can invite you for an in-person visit in the near future. And thank you.
Thank you, Jim. Thank you, everyone.